Hello, class. Welcome back. So, for today's lecture, we are covering chapter section 2.5. So, we're aiming to get through 2.5a and b. 2.5a, we're going to go back to some limit stuff, touch base on some basic limit rules. A lot of this you may already know, some of it we've already covered, but this is just to make certain that you guys know some of these basic limit rules, so that you'll be able to use them and apply them later when you're trying to solve different limits, especially if you're trying to solve some kind of derivative and you can't use the power rule or you can't use the constant rule, so on and so forth. In some of these cases, you just got to use that good old limit definition for the derivative that we had from before. And in those cases, then it's important to know how to be able to solve a limit, and using some of these limit rules are going to help you do that. So let's get started. We are in 2.5a. So this is 2.5a. And we'd like to go over these limit rules. Limit rules. So to start, before I start writing these rules down, I just want to clarify what some of these variables are going to be. So let C be a constant number. So far so good, nothing strange about that. Let N be a positive integer, so like 1, 2, 3, 4, 5. Okay, nothing strange about that either. Let A be a real number. So this is like C, it's just something constant. Whoops, let A be a real number. And then suppose that we have some function f, and that the limit as x goes to a for f of x is equal to L1. L1 is some constant number, some real number. And suppose we have another function, g of x, such that the limit as x goes to a for g of x is equal to L2. Where L1 and L2 are real numbers. Okay, so they're like A. They're just some constant number. They're the result of what these limits approach as x goes to A. Okay, so far so good, nothing weird. Now we'd like to use all of these little variables here and put together some limit rules. So I'll give you a chance to go ahead and write that real quick, because you may want to look back and say, oh, what was C, what was N, what was A, so on and so forth. So I'll give you a chance for that, or you can actually pause the video and then write it down, so that might be better. So we'll go ahead and move on. So now that we have that covered, we want to use those pieces to put together these rules. And these are things that are going to be true across the board, which is why they're going to be useful as you work through some of these problems. So rule number 1, and this I think we'd already covered before, but we're just more clearly defining what some of these rules are. As x approaches a for the function that is c, in other words, just some constant, then the limit of this is just c. There's no x's here, so x isn't changing. It's just a constant function, which means for all x, wherever you're trying to approach it, it's always going to be the same value of c. So kind of a no-brainer, no big deal, but just to clarify that it's there and that you guys know that it's there. Next, we'd like to talk about the limit as x goes to a of x. Well, what is this? Well, again, as we kind of discussed previously, whenever you're trying to take the limit of something, If you can, you want to go ahead and plug in this number, and so long as you don't get like dividing by 0 or something, that's perfectly legal, and you can do that. So that's great. So we're going to plug in A, and the answer is A. Okay, so again, maybe it's a no-brainer, but we'll keep going. The next rule, if we have the limit as x goes to a for x to some power n is a positive integer. So this is like n squared, n cubed, n to the fourth, whatever. Then again, just as up here, if you can plug in whatever value you're approaching, go ahead and do it. And more times than not, that's going to give you the right answer, so long as you don't get any weird divide by 0 stuff. So when we do that here, our answer is a to the n. All right. So next we'd like to talk about some relationships when you have multiple functions. Sorry, I'm tripping over my words there. When we have multiple functions. So here, we'd like to take the limit as x goes to a for f of x plus or minus, doesn't really matter, g of x. So here the basic idea is that if you have a function plus a function, or a function minus a function, what is the limit if I take the limit of them together while they're being added? Well, the limit has the nice property of being distributable, meaning I can distribute the limit across, and this is just the limit of f plus the limit of g. And as we defined at the beginning, what is the limit of f? Well, that's just L1. So this equals L1 plus or minus, just leave that sign in the middle, L2. And you're golden. So that's going to be important when we start taking limits of some function plus a function. You want to keep this in mind so that you just distribute your limit across the plus or minus and then keep plugging along. So this is good. I'm going to erase these ones at the top to make room, since we've already covered those. Next, what about if we multiply? Well, if I have the limit as x goes to a for f of x times g of x, well again, in this case, it distributes. And so what we have here is just L1 times L2. So nothing tricky there. Works kind of the way you would expect it to. And so we can keep moving forward. And the same with division. If we have the limit as x goes to a for f of x divided by g of x, then again, you can just do the top and bottom, leave the division alone. This is L1 divided by L2, with the assumption L2 does not equal 0. Because if L2 does equal 0, then obviously we have some problems here, and then this rule doesn't work. So keep that in mind, we still can't divide by 0 here. And then, as we keep moving forward, if we have the limit as x goes to a for some constant times a function, well, the nice thing about constants is that we can pull them to the outside and just kind of ignore them. It's not a big deal. So if we pull this constant to the outside, we take the limit of f of x, then what do we have? Well, it's just c times the result of that limit, L1. So that's not too bad. Same thing if you have powers. If we have the limit, or I should say fractional powers, if you have the limit of, and maybe you're taking the nth root of some f of x, well, again, you can kind of leave this nth root business on the outside. Go ahead and take the limit of the inside, and this is going to give us the nth root of L1. So this is nice. These are tricks that you can use when we start having more complicated functions that we're taking the limit of. and you can pull these powers to the outside and then bring them back in, so on and so forth. This is going to be nice. So let's keep going. And be mindful here that this is to a constant power. If this instead were like the xth root, well then that's not a constant number because x is a variable. So in that case, this rule would not apply. So you want to be careful of that when you're looking at this, and make sure that you're only applying it to constant powers, where n is a constant number. Alright, so let's keep going. So then this last one here, if p of x is a polynomial. What's a polynomial? Well, a polynomial is like x squared plus x plus 1, or x cubed minus x plus 3, whatever. It's some combination of x's to powers that are being added or subtracted against each other. So it's a very broad definition, very broad term, but the power of this is that for any polynomial, the limit as x approaches a for the polynomial is just if you plug it in, which makes sense because, like we talked about before, if you can, you want to go ahead and plug in a to find your answer. And as long as you don't get any weird stuff, then that will be your answer. In the case of a polynomial, you're going to be able to do that every time, which is nice. But keep in mind here that when I say polynomial, this is not with fractions. If it's a polynomial divided by a polynomial, then that's no longer a polynomial, that's a fraction instead. And in that case, you might have a 0 in the denominator, and that's bad. We can't do that. So keep in mind, this is strictly for polynomials, not fractions. So be careful of that there. This next rule, now suppose for a limit, instead of approaching some value like a, what if instead we're talking about as x goes to positive infinity or negative infinity, doesn't really matter. What does that mean? And specifically, we're looking at 1 over x. What does that mean? Well, it means when we're looking at this graph, we're trying to determine where does that graph go in the long run. As x goes to infinity, does our graph approach any number? Well, in some examples, like if we're talking about x squared, this is just a parabola, and as we go to x, as x goes to infinity to the right, our graph just keeps going up and up and up and up and up and up and up forever. In that case, our answer is just infinity. But the question we're specifically looking at here is the function 1 over x. So what happens when we divide by a bigger number, a bigger number, a bigger number, a bigger number, so on? Well, think about it. 1 divided by 1 is 1. 1 divided by 2 is a half. 1 divided by 3, 1 divided by 4, so on. But what is happening? Well, if you think of these fractions in decimals, this is 1, 0.5, 0.33, 0.25, 0.2, so on. This is getting smaller and smaller and smaller as this bottom number gets bigger. In the same sense, when we're talking about this limit of 1 over x, as x goes to infinity, this limit is going to equal 0. That's going to be a very important idea as we move forward, especially with these limits that are going to infinity. You're going to see a lot of cases where you have infinity in a denominator and maybe a constant number in the numerator. Whenever that happens, you're always going to have 0 for the answer to this limit. So this is an important rule. It's a nifty rule. You definitely want to save that in the back of your mind somewhere. You're going to want to remember that. So let's keep going. Next, let's suppose we have a generic f of x. And this f of x is a fraction, and we have some constant a sub n times x to the n. Now, what does this mean? I'm just using this to enumerate to say that a to the n is just some constant that goes along with this x to the n power. So nothing too fancy going on here. Plus a n minus 1 times x to the n minus 1 power. What does that mean? Well, again, a n minus 1, this just designates that it's some other constant, but it's not the same as a n. I mean, it could be, but it's some other constant that's to the right of this one that pairs with this x to the n minus 1 power. So we keep going. This can go on for quite a while until eventually we get to a sub 0. This is just a constant and it has no x terms. We can do the same thing on the bottom. Let's say we have b sub m x to the mth power plus b sub m minus 1 times x to the m minus 1 plus, that can go on for a while, b sub 0. What is the point of this? Well, writing a function like this is just to, it's one way of how to abstractly write a polynomial divided by a polynomial in abstract terms. So this could be like, say, x cubed plus x plus 1 divided by x squared minus x plus 2, something or another. In this case, an is just the first coefficient on your highest power, is 1, n is 3. Well, for this middle guy where we have n minus 1, that would be x to the second power. We don't have an x to the second power in the numerator. Well, that means that a sub 2 is 0, so there's no term there. But for this next one, we have the first power and a coefficient of 1, and then we have a of 0 is 1. Same thing for the denominator. The whole point of writing this way is that it's a way to abstractly talk about all functions that match this format. So that's what we're talking about here. And the reason I write it in this format is because this is going to tell us a lot about the limits here. So, oops, dropped my pen. So, what we're looking at is if I'm trying to take the limit of a function that looks like this, and more specifically, if I'm taking the limit as x goes to infinity for this f of x, what does this mean? What's happening? Well, it depends. If n is bigger than m, in other words, if your polynomial in the numerator has the biggest power, it has the x with the biggest power, then in that case, the answer to your limit is going to go to infinity. Why? Well, that has to do with the fact that n is the bigger power. So in the long run, as x gets bigger and bigger and bigger and bigger, this higher power in the numerator, when we raise to the third power, fourth power, fifth power, whatever this power is, it's a bigger power than the guy in the denominator. So this numerator is actually going to grow more quickly because it has a higher power. And if the numerator is going to grow faster than the denominator, that tells us the numerator is going to take over in the long run. And once the numerator takes over, well, it can just keep increasing forever. There's nothing to divide it to make it smaller. And so, the limit in this case, when the bigger power is in the numerator, the limit goes to infinity, or in other words, does not exist. But what about the opposite case? What if m is the bigger number? In other words, the biggest power for this entire fraction is attached to an x in the denominator. Well, then the reverse is true. That means our denominator is growing at a faster rate than the numerator. And if your denominator is getting bigger and bigger and bigger faster than your numerator is, then it's just like this example of 1 divided by x. Your denominator is going to take off and explode. And if your denominator is getting way bigger than your numerator, then your answer is tending to 0. And that's exactly what happens here. Then the limit goes to 0. But what if they equal each other? That's the last case we'd like to discuss here. If n equals m, so we have the same power in the numerator and denominator, then what happens? Well, in that case, the top and bottom are increasing at the same rate. Neither one is increasing faster than the other. And so these infinities, in a sense, because we're dividing, end up taking each other out. And so what number do we approach? Well, in that case, we approach the number that creates a fraction using the coefficients on whatever that biggest powers were. So in this case, it's the an divided by bm. That's what our limit is going to tend to as x goes to infinity. Now these rules here that I just used to apply to this generic function that's a fraction, this is going to be very important. You're going to be using these kind of ideas over and over again for the rest of the class. The thing to keep in mind, though, is that this is specifically when we're talking about limits where x is going to infinity. If we're talking about examples where x is going to a, like in some of these other rules we have, then this does not apply. Don't do this. This only is in the case where x is going to infinity. So keep that in mind so that you can apply these tricks and rules appropriately where they're supposed to be used. All right, so there we go. That covers the vocab I wanted to cover for 2.5a. So now let's talk about some examples that are using these rules we've discussed here, so that you can actually see how they work out. So let's give it a go. All right. So let me clear the board again. All right, here we go. So example 1. Example 1. All right, some factoring simplification. Okay, let's suppose we're looking at the limit as x goes to 2 for the function x squared minus x minus 2 divided by x squared minus 4. Now when we think about this, the very first thing we want to do is, can I plug in 2? If I can, then great, there's my answer. However, in this case, we can clearly see that if I plug it in, for my denominator, I'm going to have 2 squared minus 4, which is 4 minus 4, which is 0. I'm going to have a 0 in the denominator, which is bad. We can't do that. All right, so I can't plug it in yet. I've got to do something else. So what else can I do? Well, you may notice that the denominator is of the form x squared minus 4. But what is 4? Well, you can think of 4 as 2 squared. In other words, we have a perfect square minus a perfect square. Keep in mind that anytime you see something of the form a squared minus b squared, something squared minus something squared, you can always rewrite this in terms of its conjugates. What are conjugates? Well, that's where you take a and b and then you flip the sign in the middle. You can always factor a squared minus b squared like this. A plus b times a minus b. And if you double check me and multiply this out, the middle terms that you would normally get when you multiply two binomials are going to cancel out. So this is a nifty trick to keep in mind when you're looking at something squared minus something squared. So what does that mean in this case? That means my denominator I can write as x plus 2 times x minus 2. Okay, so far so good. But what can I do to the numerator? Well, let's try to factor this. We've got an x, we've got an x, it'll have to multiply against each other. We got a 2 on this side, so we'll have to have 1 times 2. Those are the only factors of 2. But what sign do I put in here? Well, I want to have a negative 1 in the middle. Well, if I do 1 minus 2, so I'll need a positive 1 minus 2, that'll give me negative 1. And we're good. We factored it, and now we can cancel these like terms in the numerator and denominator. And we're just taking the limit as x goes to 2 for x plus 1 divided by x plus 2. Now I can plug in 2 without any problems, and I'm going to have 2 plus 1 is 3, 2 plus 2 is 4, and there's our answer, 3/4. So not so bad, but that tells you how to get our limit in this case. So let's keep going. Let's look at another example that uses the same kind of trick, but is not easy to pick out. So let's suppose we have the limit as x goes to 100. And this is the square root of x minus 10 divided by x, let me make sure I copy this right, yeah, x minus 100. So we can see here that if I try to plug in 100, 100 minus 100 is 0. Well, that's bad. I can't do that. But we can go ahead and double check because we had a rule from before when we talked about limits. I believe it was a few sections ago. If you have a fraction that gives you a non-zero in the numerator and a 0 in the denominator, then the limit doesn't exist. So we should always be double checking that before we try to simplify. However, in this case, when I plug in x equals 100 in the numerator, I'm going to get square root of 100 is 10, 10 minus 10 is 0, and so I have 0 divided by 0. So that's indeterminate. It doesn't really tell me anything about it. Okay, so we had to simplify somehow. So what can we do here? Well, the tricky thing with this is, notice we have 100 here, which is also 10 squared. Okay, so that could be helpful. We've got this negative here, so we could maybe get something with this a squared minus b squared business, but we've got to write x different before we can apply this rule. Well, what is x? One way to think of x is the square root of x raised to the second power. So why do I write it like this? Well, the square root and then squaring on top of it, they really just cancel each other out. And this is the same thing as x. So these are equivalent. But why did I write it this way? Well, now that I've written it this way, I have something squared minus something squared. Well now I can apply this rule with conjugates. So this is equal to the limit as x equals 100 for the square root of x minus 10 divided by, and by conjugates, I have the square root of x plus 10 times the square root of x minus 10. Now I can cancel like terms, and I'm really just looking for the limit as x goes to 100 for 1 divided by the square root of x plus 10. Square root of 100 is 10, 10 plus 10 is 20, And so our final answer is 1/20th. And there you have it. So in the case of this question, how did I know to try to do this weird conjugation trick? Honestly, it's just a matter of practice. The more you look at these questions and the more you kind of play with the algebra of how you can simplify these guys, you'll start to get a little bit better and faster at this, and you'll be able to simplify this guy a lot quicker. And unfortunately, there's no secret trick other than just practice and looking at these guys more often. So there you have it. That's how you would do a question like this that isn't immediately obvious. I'd like to do... let's do 2 more quick examples. And then we'll move on to 2.5b. So, all right, here we go. Let's consider the example. The limit as x goes to negative infinity for x cubed plus 7 divided by x squared plus 9. Well, in this case, we're talking about infinity, so we're approaching not some constant number a, and we're dealing with a polynomial on top of a polynomial. This is like our example in that special case of when we need to look at the powers. Well, notice here, 3 is bigger than 2. So what does that tell us? Well, that tells us in the long run, the numerator is going to take over and blow up to infinity. All right, so we know our final answer should be infinity, but should it be positive or negative? Well, let's look at the signs here. We're plugging in negative infinity, so we're going towards the negative direction. Well, negative direction, that way. But a negative squared is going to be positive. Plus 9, we have a positive in the denominator. So positive sign in the denominator. But in the numerator, we have a negative cubed. A negative cubed is still going to be negative. Plus 7, well, the plus 7 doesn't matter because this x cubed is going to get so big. So we have a negative divided by positive. In other words, our answer is negative infinity. And there you have it. Or in other words, you would say it does not exist. And we're good to go. And then as a final example to go along with these examples of fractions, suppose we have the limit as x goes to infinity for 4x squared plus 9 divided by 5x squared plus 2. Well, in this case, note that the powers 2 and 2 are the same. We have equal powers. And so when we have that happen, that means the numerator and denominator are growing at equal rates. They're both growing equally. So the infinities for the top and bottom are kind of going to cancel each other out. And what are we left with? We're going to be left with the coefficients on the end. 4 divided by 5. And that's it. That's your final answer, and it's that easy. So this will save you the time of when we're talking about limits that are going to infinity, you can quickly kind of tell and look at it based on these powers what your answer should be. And it'll save you the headache of trying to simplify these guys, because oftentimes maybe you can't. Maybe it's not that you can't, but maybe it's just not possible to simplify them. And so there you go. There's 2 examples using the case where x goes to infinity. All right, so that covers 2.5a. So now we'd like to close up today's lecture with touching on 2.5b. Now for this one, there's more just kind of definition stuff. Not as many examples to work through, so this won't take as long to get through. All right, so what are we talking about? What are these definitions? So the first thing is, remember continuity when we talked about what it means to be continuous. Continuous. We discussed this before. The definition we gave was that when the limit as x approaches a from the left for f of x equals some value, well, it equals what f of a is, but the same thing happens from the right side. In other words, for our function, as we approach this point a, the lines meet together at the same point. But not only do they meet at the same point, they meet at the point that the function actually equals there. So they're all fully connected, and so we call that continuous. In general, we say that a function is completely continuous, the entire function is continuous, if it's continuous at every point, for every possible a. So what does this mean? It means no holes anywhere. In the case where they meet, but f of a is like maybe up here, which we had examples of that where maybe your picture looks like this. You got an open circle, it keeps going, but the real point is somewhere up higher. We also say there are no jumps. Well, what's a jump? Think about our piecewise functions, where we got a graph and then it stops and then it picks up somewhere else and keeps going. This would be a jump. And then lastly, we say that there are no vertical lines. Or I'm sorry, not no vertical lines, no vertical asymptotes. Asymptotes. And what do we mean by that? Well, recall our example from before that we keep referencing back to. We had a vertical asymptote for x equals 1 and a horizontal asymptote for y equals 1. Our graph, we kind of had this shape on the left side, and for the right side, it went down. In this case, we had a vertical asymptote at x equals 1, and so quite clearly, the function is not continuous at that point. So there we go, definition of continuity. But we'd like to further clarify what it means to be continuous. So what we mean here is to be continuous means all of the following are true. And so what am I talking about here? Well, 1, f of a exists. That means the point at f, or the point at a for the function f, has to exist. 2, the limit as x goes to a for f of x, the limit also has to exist. And lastly, not only does the limit exist as x goes to a for f of x, but it has to equal whatever f of a is. If all of these three things happen, then the function is continuous at a. Okay, so far so good. So what do we have when this doesn't happen? When this definition breaks, this is what we call discontinuity. So if the limit as x goes to a from the left is equal to some L, which is not equal to f of a, which is not equal to L, which maybe the limit from the right side equals. So in this example, whoops, left off my f of x. So in this example, the limit from the left and right sides equal each other. But they don't equal what f of a actually is. They don't equal the point the function actually is. This is an example of what's called removable discontinuity. removable discontinuity. Why do we call it removable? Well, this is like our example where we got some function, it meets at a point, open circle, and then continues on, but the real point is up above. It's only discontinuous at this one point, and if I could pick up that point and move it back into the open circle, then suddenly it would be continuous. And so we call this a removable discontinuity, because if I can move the point, then it wouldn't be discontinuous. But we have other examples. Suppose that in another case, the limit as x goes to a from the left of f of x does not equal the limit as x goes to a from the right of f of x. This is an example of a jump discontinuity. So again, this is kind of just touching on again, what do I mean by a hole? What do I mean by a jump? And we're applying labels to those types of discontinuity. You may encounter some Hawk's Learning questions where they ask you, what is a removable discontinuity? What is a jump discontinuity? What are all the points of discontinuity for a function? That's where you come to graphing it and you want to find where this stuff is happening. So this is a jump discontinuity. And then the last kind of discontinuity, if the limit of f of x as x goes to a is equal to positive or negative infinity, doesn't really matter. In either case, this is what is called a infinite discontinuity. Discontinuity. And in this case, we say that the discontinuity is non-removable. Why? Well, it's not just the case of a single point is out of place. I can't just pick it up and move it. In the case of an infinite discontinuity, for example, a graph that looks like this, where as we approach 0 from the left and right, it goes to infinity, I can't just pick this up and modify it to make it suddenly continuous. And so we call this an infinite discontinuity, or in other words, a non-removable. You can't move it around, so it's a non-removable discontinuity. So there you have it. That covers the gist of what we wanted for 2.5 A and B. Now I realize we didn't do any examples for, here's a function, find the points of discontinuity. But more or less you guys already know how to do that. Especially if we're dealing with fractions. If you find points where the denominator is 0, then that's a point of discontinuity. If you find points where when you graph it, you see that it zooms off to infinity from both directions, then that's a point of discontinuity. So you already know what to look for when you're dealing with these questions. It's just a matter of applying what we've already learned up to this point. So that covers everything I wanted to have in this lecture video. Of course, if you have any questions, concerns, don't hesitate to email me. We'll talk about it. And of course, we're going to have our Q&A later in the day, and we can more directly discuss any questions you guys may have. So that's all I've got for you, and I wish you guys the best of luck.